Oh, good afternoon. We are continuing our interviews with SIGGRAPH pioneers, and today we're meeting with Nick England, one of the electronic geniuses who helped convert vectors and pixels into images that we could all see and enjoy and use and marvel with. So Nick, the way we're beginning most of these is I'm asking you your name, please.
My name is Nick England.
And when were you born?
I was born in 1947.
Aha. And where?
Actually in Richmond, Virginia, but southern part of Virginia is mostly where I grew up.
And tell me a little bit about your parents and your growing up time.
Well, let's see. My mom had been a school teacher before she got married. She did a little bit of substitute teaching after that, math teacher in junior high, I guess. My dad was worked for the power company. He originally was a lineman, would go up and do repairs and installations on telephone poles or power line poles, and then became a supervisor. So that's what it was like.
What did you do in, where'd you go to grade school, high school?
Well, originally my dad was stationed in Gloucester, Virginia, which is just north of Norfolk, Virginia. And so I went there through the third grade. And then we moved to Elizabeth City, North Carolina, which was just south of Norfolk. He was transferred there. And that's where I finished high school. So all the way through high school there. So most of that was in Elizabeth City. It's a place on a river, about 60 miles from the coast, I guess, but it's a flat, uninteresting territory.
What were your passions in high school?
I guess early on, I started getting interested in science kind of things. Early chemistry set and created smoke in the house and, ended up burning things and stuff like that. Electricity, motors, generators. And then I got into ham radio when I was in, I don't know, maybe the 9th grade, 10th grade. A friend down the street got me interested in ham radio. And that really was, in terms of a passion, I guess that was it. Outside of the normal passions that a teenage boy has.
Did you build your own station?
Yeah, I built a bunch of stuff. Some of it was war surplus. Some of it I got in kits from companies like Heathkit and Knight-Kit that made electronics kits for people to put together. And some of it I built from scratch based on articles in handbooks and magazines, that sort of thing. Got a lot of help from local ham radio operators, people that were in probably I'm just guessing now, probably in their 30s, some in their 50s, but they were really helpful to us kids that were growing up. We got parts, we got, helpful hints. They had test equipment. We could come try to debug and make our stuff work. So a lot of encouragement from those kind of folks.
So do you know how to do Morse code?
Yeah, but I don't do it much anymore. I mainly mess around with teletypes these days instead of Morse code.
Was that vacuum tube gear or transistor gear?
Oh, I stick to, for fun, I stick to vacuum tube gear. And that, of course, that's mostly what I had back as a kid. It was only much later that I got into things with transistors and integrated circuits.
And in college, you discovered you favored electronics more.
Yeah, well, that was why I went to college, I guess, in electrical engineering, is because I wanted to learn something about electronics and, how to design this stuff and why it worked. And so I went to school in electrical engineering at North Carolina State. And it was mostly analytical rather than design oriented. And so I didn't do very well. I wasn't interested in learning all about Maxwell's equations. I wanted to learn how to make antennas. Now you need to know Maxwell's equations in order to make good antennas, but like I said, I was more interested in the design part of things. It was only later that I really got a chance to do that.
How important was mathematics in this education?
Oh, well, it's the fundamentals of everything. Mathematics gives you the model that you can then determine what's going to happen in a circuit or in a system, anything. It's
When did
it's
you
so
first
important
encounter?
that they started off, because I had good grades in high school, they started me off in a theoretical mathematics curriculum. And that was useless as an engineer. I could prove things, regular mathematics proofs, but I couldn't use it in order to solve problems, which is what I really needed to do. So eventually I transferred into a different line and got more practical mathematics, good for engineering work.
And do you consider yourself an electrical engineer, a computer engineer, a mathematician?
Definitely not a mathematician, no, not a scientist, but well, electronics/computer engineer, I guess. Originally just electronics, and I just worked in communications electronics for a while, but then I went back to school and really got involved in computer engineering and digital systems design.
When did you discover your first integrated circuit?
Let's see. I remember reading about them in undergraduate school and thinking, my gosh, they've got 19 transistors in this single little package, and it only costs $45. Who could imagine such a thing? But I don't think I ever saw one until later on. And then I got a chance to start building some things when I was, I don't know, a year or so out of school.
So after the between the ham radio experience and kind of what we might call the image display, what did you do in between those two sort of junctures in your life, electronically and computation?
Well, I worked in communications electronics, so transmitters and receivers used for voice or data. And that was the first time I got to use a computer, an interactive computer. It was just a Model 33 teletype hooked up to a HP time sharing system, and wrote some basic programs and things like that. But that sort of got me intrigued about computers might be useful for something.
And this man Stoudemire, is that I pronounce it correctly?
Oh, Staudhammer. Yeah. So Staudhammer, John Staudhammer. When I was an undergraduate, I had been going out to a local junkyard that had surplus IBM equipment, and I acquired and built up in my dorm room a 7-track digital tape drive. I mean, one of these monstrous things that you always see like in a science fiction movie with the reels moving back and forth and everything. Well, I had accumulated the pieces and designed the logic circuits. Mostly it was relay logic to control it and had it running. And John Staudhammer, who's a professor in the EE department, and he was pretty new there, I guess, at that point, had been given a digital tape drive as a donation, and he wanted to get it working. So he heard that I knew something about this. So I got a summer job with John, my last summer as an undergraduate, and restored this thing. It had, I think, about somewhere around 70 vacuum tubes and 120 relays in it. So I got a real immersion in digital logic. Now, it was ancient digital logic, but it's all the things still applied in working on that thing and getting it to work. So when I went back to school three years later, I looked up John, hoping that I could get a part-time job just to keep things together. And in the meantime, he had gotten a grant to build up a computer graphics research program. So I walked into his lab thinking, well, maybe I can repair some computer equipment for him. And he's got rotating images up on a screen. You turn a knob and this thing rotates. I was totally hooked and always have been.
So you're from a generation that in your youth, you had vacuum tubes and transistors, and in your adulthood, it was a digital world. So could you share a little bit about this transition that we went through from analog technology and oscilloscopes into using digital circuits. How did that change things? How is it different? Why was it significant or important?
Wow. Well, I guess the main thing is one of scale. You can build a radio out of 5 tubes or so, and you can build a radio out of 5 transistors. You remember possibly the first portable transistor radios advertised 3 transistors, 4 transistors, whatever. Essentially, they did the same thing as tubes, except they were smaller and lighter and took less power and all those kind of benefits. But the great thing was, instead of having to build a computer that took 1,000 tubes, 2,000 tubes, and took up a huge building, all of a sudden you could build a computer that was a lot smaller, and you could put in hundreds of thousands of transistors, and eventually, obviously, millions and billions of transistors. So the just being in the right place at the right time, as the technology shifted from, you could make a computer, but it was a national effort to make a computer, to you can make a computer, it's just an Arduino or whatever. It's nothing much to do. I was kind of in the middle of that. I made computers. It was a graphics computer, a programmable graphics computer that was sort of in the mid-range of it. It still took a fair amount of size and a fair amount of power, but I could do it. Whereas 10 years earlier, there was no way in the world that anyone could do it.
Do you know how to program microprocessors?
Yeah, I mean, I have done a lot of that. Not recently. I got more into doing other things.
So an electrical engineer and a computer programmer, what's the...
Oh, well, we had, John Stonehammer created this wonderful lab. We didn't really make much difference between hardware and software. If you needed a piece of hardware, then you could just build it. If you needed some software to do something, you'd write it. Obviously, software has all the flexibility in the world, and you can do pretty much anything. But if you want to do it fast, you might need a piece of hardware in order to do it. So we built hardware, we built software, we built interfaces to weird gadgets, joysticks, tablets. All these things were required engineering, digital engineering, in order to interface to some sort of computer back then. Nowadays, it's plug and play, and software takes care of pretty much everything you want, except for the folks, somebody somewhere has got to design that gadget. And that's what electronics engineering is about, is designing the gadgets. But it's all intermelded. I think one of the things that was interesting is we tended to look at software design like we did hardware design, that it was very modular and it had well-defined inputs and outputs. So we shared code a lot. I mean, somebody would write something for a modeler or a little animation piece or something like that. And somebody else would be able to pick it up and use it quite easily because it was all pretty clearly defined. I don't know if you call that software engineering or not, but it worked out really well.
So what prompted you to go to graduate school and get a PhD?
Well, I never got a PhD. Instead, I built a gadget that was going to be my dissertation project, and we built and sold 400 copies of it, I guess. Actually, I went back to school at NC State because I had met Mary Whitten, and she was in grad school there, and I moved back to Raleigh, where North Carolina State is. But I also wanted to find out something about computers, and also wanted to go to some classes that I never had a chance to as an undergraduate, because you were pretty focused on taking your engineering and mathematics and physics courses and going on out. So I took some history of architecture and art history and philosophy and some things like that, just as a chance to kind of catch up on what I might have missed. But mostly my time was spent working in the lab and designing things and working with other students. I was just lucked into the greatest thing in the world, as far as I was concerned.
We should establish probably that where you went to school, and I'll develop that a little bit with you.
Okay, well, I went to North Carolina State University, which is in Raleigh, North Carolina. It's the land grant college, big engineering school. Electrical engineering department is probably one of the largest departments on campus, I guess. And that's where I went back to and took a lot of graduate courses. I took all the graduate courses, and they let me into the PhD program because I'd taken all the courses and gotten A's on them and had passed the written exam for a PhD, but I never finished it. Mary and I started the company instead.
Now, you went to University of North Carolina, or you?
No, no,
No.
don't confuse those two. University of North Carolina is the liberal arts college, and NC State is the engineering and agricultural school, basically. So it's like University of Michigan and Michigan State, or I'm sure there are parallels all around the country between the land grant colleges and the other universities. So interestingly, yes, UNC had a graphics program and it was pretty well known, but at the first SIGGRAPH conference, NC State had 4 papers and UNC had none.
Now,
So you never know.
Did you meet Fred Brooks in your passing?
Yeah. So, we're only 25 miles away. So if there was an interesting seminar or something, we would, several of us would drive over to UNC and go to a seminar. So that's where I first met Fred. And I met Henry Fuchs at a SIGGRAPH conference. And then Henry joined the UNC group there. And so we ended up going over a lot more often then. And he was one of our earliest customers for this hardware that I built.
What was your PhD thesis about?
Well, it was building a programmable graphics processor. It grew out of a research program that was funded by NASA to develop innovative cockpit displays. So like you can imagine a highway path through the sky, a 3D highway path through the sky for landing. And the pilot would try to fly down that. But basically, what the idea was try to get away from vector line drawing graphics, which is what pretty much everything had been, to raster graphics. And I talked my way onto this research project and first built a dedicated piece of hardware to essentially to draw lines, but to draw them on raster displays. So on TV screen like displays. But then some technology came along that allowed me to build a programmable processor that would run just as fast and was a heck of a lot more flexible. And that was really, really interesting to me because then I could use it to do anything. And a point of fact, that turned into a product in our company, and software got used to do lots and lots of interesting things.
And what year was this about?
So this would have been 78, 77, 78. That's 1977, 1978. I went to SIGGRAPH in 77. That was my first SIGGRAPH conference. It was just awe-inspiring. I saw so many people doing so much interesting stuff. And part of it, I came back and said, well, I got somehow or other, I've got to get a paper into this. And I had a really interesting device that I was working on. And I had a really interesting idea about how to use it in what was a really early augmented reality system for creating models of interactively creating models of real objects. So that was a paper that I had in SIGGRAPH 78. And then Mary and I started the company in the back room of our house in 78.
We sometimes think of the origins of computer graphics at like Bell Labs, MIT, maybe Magi, General Electric in Syracuse, Utah. And sometimes your part of the world is not mentioned in the short list, but maybe we should mention it, and you might like to add a few other places that also deserve some of the early inspirational credit for as we develop forward.
Well, so one of the things I remember seeing at SIGGRAPH that was always inspirational were the animation work that came out of Ohio State, Chuck Suri's group at Ohio State. That was all really interesting. There was a lot that happened here in North Carolina, both at NC State and at University of North Carolina. In in modeling, scientific applications, image processing, hardware development. So lots of things came out of there. Other places around the country that don't make the usual list. We were all jealous of Utah, of course. That seemed like the place to be. And
You
lots
call-
of things were happening.
You call what you built early on a frame buffer, or you have a different name for it, and why so?
Well, a frame buffer is the memory array that holds a frame of pixels, an array of pixels, right? Now something's got to create an image by flipping the bits inside those memory cells that make up each pixel within the frame. And that can either be a general purpose computer, or in my case, it was a special purpose computer. Well, it was a general purpose computer that was optimized for doing graphics and imaging type operations. So it could do things a lot faster than a general purpose computer could for two reasons. One, it was intimately, tightly coupled with the display, that is the frame buffer that was going to put the picture up on the screen in front of you. And the second was that I had thought about what kinds of operations you needed to do quickly in order to create images. For example, if you're drawing a line through an array of pixels, well, you draw along a line, and then you got to move up a little bit and draw along a line a little bit up like that. So you get a slanted line, right? Well, that's an iterative process. You draw so many pixels this way, and you move, and then you draw so many pixels this way. There's the classic algorithm, Bresenham algorithm. The computer that I designed and made, would do that in one instruction. It was a one instruction loop. It didn't go add this thing, test this thing, write this pixel, test whether you're done or not, and then do this. It didn't have to execute like 8 instructions to draw a pixel. It executed one instruction over and over again, just because it had hardware that counted the loops, some hardware that tested the results, and hardware that wrote the pixels, and all this happened in parallel. So it did a lot of things in parallel, but it was still programmable. So it ended up being really, really fast for lots of things.
There's a line drawing algorithm by a mathematician from IBM whose name escapes me.
Jack Bresenham.
Yes,
Yeah.
sir.
Yeah.
And you implemented that?
Yeah, that was exactly what I did, was implement the Bresenham algorithm, and it ran in one instruction, just repeated itself over and over, and then it would periodically jump to another one instruction, but it never did more than one instruction.
When you do parallelism like that, do you try to do it with a computer, or do you build special hardware to do it?
Well, you had to build special hardware. A general purpose computer, even a parallel computer, maybe could do some of that stuff. We're having a heavy rainstorm here, so if you hear a funny noise, that's what it is. Anyway, a parallel computer usually can only do a certain range of things. And because I wanted to do graphics and imaging type operations, a general purpose parallel computer wasn't really the way to go. This was a specialized computer that had parallel functional units. So it had a loop counter, because I needed to do a lot of loops. It had another loop counter, because you need to count loops in X and Y, right? It had pixel writing capabilities, because you need to write lots of pixels. It had, adders and subtractors and things like that. But these all happened in one wide instruction word. So instead of being a 16-bit instruction or a 32-bit instruction, this was a 64-bit wide instruction that controlled, 8 or 9 different functional units all at once. It seemed to me the way to build something.
Did you have a hard time affording memory chips in the early days?
I built this machine as a graduate student right when 16K by 1 chips came out. It's only 16K bits total. They cost $55 a piece. It was, nowadays, 16 megs, 16 gigs, it doesn't matter. It doesn't cost anything. But but it was a lot better than having 4K chips, which is what we had before. So we go through these iterations, and I was lucky enough to be at one where the technology made something affordable that wasn't affordable just a year earlier.
So after graduate school, you formed your own company.
Yeah, well, it was sort of during graduate school, I guess. John Starnhammer had built special purpose hardware for a couple of people. He built a frame buffer. That is, it was just a dumb frame buffer. It didn't have any processor in it, for the University of Miami Oceanographic Research Group. And he built a specialized graphics processor for Chuck Suri's group at Ohio State. And he built this in the basement of his house with some grad students helping out. And I said, enough people asked me about my graphics processor and display system, if they could get a copy for their lab. Then I said, well, maybe we should do a company like John's or team up with John. Well, John had come to his senses and he didn't want to do that anymore. But Mary and I decided that we would do that. Our business plan was we would build maybe 4 or 5 of these machines, because that's all we figured, the number of people that were crazy enough to want one. And then we take whatever money we'd made and take a vacation to Europe and then come back and get a real job. That was it. Well, 400 or 500 machines later, we finally got to go on a European vacation.
Which was more difficult, making the equipment work or trying to run a business and stay liquid financially?
Oh, me, oh my. Well, I knew a lot more about making the equipment work. It was hard, but I knew a lot more about it. Yeah, we got help. It was an interesting experience. It was.
Now you discovered SIGGRAPH in the middle to late 80s, right? Or the middle to late 70s, early 80s?
Yeah, I went to my first SIGGRAPH in 77. Some other people from the graphics lab at NC State they presented papers at the first one in 74, and other people had been in 75, 76. And I don't remember why I didn't go. But anyway, in 77, went to SIGGRAPH in San Jose and was just gobsmacked. You know, it was so many intelligent, smart, creative people, and the energy level was so high, and I was seeing so many wonderful things like the triple-I demo reel and outtakes from Star Wars, Larry Kuba's rotating Death Star. And these were the earliest animations that people were doing, and that was really cool. And there was hardware, and there were people doing new algorithms. It was just incredible high energy thing. It really was.
And in short order, instead of being a wide-eyed novice, you became a hardened regular.
Well, I guess so.
Pioneer.
In 78, in SIGGRAPH Atlanta, I presented a paper on this system that I had built, and a number of people came up and said, that's pretty interesting. We'd like to get one of those. And that eventually turned into systems that we built for other researchers. Then in 79, we did our first exhibition of equipment, and we did that for years on. Then we got acquired by a larger company, and I stayed with them for a while. And then Mary and I and Tim Van Hook, who came out of Ohio State, but came to work with me in Raleigh, we started another company. So exhibiting and presenting papers and being on panels and conference committees, papers committees, it was my life for more than 20 years, I guess, 25 years, long time.
Walk us through the developments of the 80s and 90s there, and because that was a rapid in terms of pixel displays, and later combining them with vector graphics in behind them. There was and resolutions, and also you never really made machines that output to video. My NTSC, composite type video.
Oh, yeah.
No?
You're well, we had to use an external encoder, but one of the things that I really paid attention to was NTSC compatibility, including all the stuff about acceleration pulses and equalizing pulses and all the funny little things that happen in a vertical interval, getting gen lock so that you could sync to external sources. And we got used a lot for people putting stuff onto good video. The first one of those was Marks and Marks, animation company in LA, and they hired Doug Kay and George Joblove, who came out of Don Greenberg's program at Cornell, but then had moved to Dallas, and it had a little work on our machine that we made, which we had delivered to a medical imaging customer in Dallas. And so they worked on it there. Anyway, when they got out to the West Coast with Marks and Marks, they said, we need a frame buffer that does good NTSC and that we can create things on. So they bought one of the first ones that were used in the animation world. We ended up with a whole bunch of machines in the LA area for people doing animation and people doing real-time, well, not real-time NTSC, but frame at a time NTSC with gen lock and all that sort of stuff. I mean, you ask about what the technology did during the 80s. Well, increased resolution, display screen resolution was one thing, but it was also the era when you could start making custom integrated circuits. So the whole premise that Silicon Graphics was built on was using custom silicon to do specific functions, transformation, drawing, and to do it at incredible speeds. The driving application at that point, I guess the driving applications were two. One was computer-aided design, where what you really needed to do was lots of vectors, but you needed to do them on a screen that you could afford, which meant a regular CRT screen, a raster display rather than the early vector displays, even though you were just doing line drawings for computer-aided design. And then it started becoming color models that people would do, solid modeling applications for computer-aided design. And then animation was the other big driving problem. And that mostly happened on the software rendering side of things, not so much on the hardware side, except people wanted more compute power. That was what happened there. But eventually it got so that creating custom silicon became something that lots of people could do. And that's where, to my mind, the huge change happened that frankly, I don't think anyone saw coming, and that was games. Games drove graphics technology like nothing. I mean, it was just like somebody had lit a fuse on a gigantic Saturn V booster rocket or something. And all of a sudden people were doing things because they could afford to put their engineering resources into it. And the chip technology had developed to the point where you could create these things with millions of transistors. You could put things on a small board and plug it in your computer, and it could do stuff that machines of only 2 years earlier could only dream about. So that was, to me, from a hardware standpoint, and none of the computer-aided design people, and I don't think the animation people either, saw that what was going to happen. Now, of course, what we have are graphics processing, programmable graphics processing units, general purpose GPUs, and that has revolutionized rendering for animation applications. Wow, games drove a lot of stuff, and I certainly never saw it coming, other than putting quarters into machines. That was it.
You sold companies, you founded, and you've started new companies. Why that kind of modus operandi for you?
Because I don't have any better sense, I suppose. Well, I think the companies that we started, and there were three that I've been involved in, were because we couldn't stand to not do it. I was a grad student. I had done something I thought made a really great tool for other people to use, and other people were coming to me and saying, how can I get one of these? And the only way they were going to get one was if I built it for them. So Mary and I started the first company to do that. The second company happened when we saw the big transition away from mini computers to desk side workstations, Sun Microsystems, Apollo, other people that were making, very powerful computers, mostly for engineering applications. But they were smaller and more affordable and not quite personal computers, but if you got hold of one, you didn't let it out of your office, right? So we made a programmable graphics processor that would plug into Sun Microsystems workstations, and Sun bought us. After that, I got tired of trying to be a manager because I really was an engineer. So I went to join Henry Fuchs and John Polton's lab at UNC, at University of North Carolina. They had built the Pixel Planes series of machines and were working on one called Pixel Flow. And I worked on that for 7 or 8 years, but I kept on seeing, again, I just couldn't stand it. I kept on seeing nifty technology getting developed and people wanting it, but it not getting out into the real world. So I started up another company to commercialize some of the technology that had been developed at UNC. And that was the third and final episode in doing that.
Did you do all the designing yourself, or did you have other engineers and computer programmers working with you?
Oh, well, the original machine, I did all the hardware design on. The one in the research machine in the lab, the prototype, if you will. And one of the other professors, Ray Stroh, wrote a compiler for it, so we could write code for it. And then I wrote the only code that ever got used for anything. Then when we started the company, Mary designed some of the hardware. We hired a couple of other hardware engineers. I did the architecture and all the original sort of the guts, the basics of it, and designed that personally. But the other pieces were added by other folks. And then in the second company, Tim actually designed hardware, but we all worked on the architecture, what it's going to do, what it will do well, how do you organize it to make it do those things. But other people did that. And, obviously lots of people writing software for stuff. We wrote all kinds of things, interesting stuff.
How do you feel now as a man in your 70s talking to another 70-year-old on a computer screen in real time with video, with 100 other things going on where we are thousands of miles apart? Are you dismayed? Are you elated? Are you depressed?
Oh, I think it's wonderful. I think it's great.
You feel overrun? I mean, emotionally,
no,
how do you?
It's
Having helped create the monster, I mean.
Well, it's certainly a lot easier to just go buy something nowadays than it was to actually design it and build it because it didn't exist. No, boy, the tools we've got now, and I'm just amazed at what we can do on our phones. I got rid of my 35 millimeter cameras because I just take photos with the phone cameras, which are really great.
When we go to SIGGRAPH, we see images that are beyond what I can't speak for you, but we see images beyond what we could comprehend was possible when we were younger people. And, where are we in terms of the state of the art right now? Are we at a plateau and we've crested and now it's all just the tools are so perfect that all we need to do is use them, or is there still developments to be had?
Do you think you're talking to a person right now or to an animation that's running on a GPU with an AI engine behind it, trying to make sense of what it's saying? We're getting close to the point, maybe, where you can't actually tell. There's a lot to do. There's a lot to do. But what we can do in terms of human animation, for example, in real time, and the combination of AI and sort of explicit computing is just sort of beginning to get started, I think. You know that NVIDIA introduced real-time ray tracing for the gaming and stuff. It's great. They don't trace all the rays. They use AI to figure out in between the rays that they do trace. So there's an intriguing combination there. But what's going to happen? I need a jack to plug right into here. I mean, virtual reality systems today are like the graphics systems of the 70s were. They're really crude. Yeah, you can see it. I mean, we used to be really satisfied if you could turn a knob and see something in line drawing move, right? And then a little later, it was turn a knob and something that was shaded looking object can move. Now we want it so that you cannot tell the difference between a live video and an animation or a real-time generated image. But we still need, the jack in the back of the base of the skull or whatever.
Yeah.
So that we can have a real virtual reality experience.
Do you think virtual reality is a myth, or is it something that's going to become a part of the media landscape in a significant way?
That gets to talking about consumer issues. And I am the world's worst when it comes to thinking about anything about mass markets or anything like that. All I've ever been able to do was occasionally predict things that would be useful in a research lab or in, an advanced technology application, something that's really tough to do, for example. But in terms of what's going to appeal to consumers, is it going to be the immersive experience, or is it going to be a new form of storytelling so that it's different from the kind of things that we do in 2D? I don't know.
I felt when I first discovered SIGGRAPH, I felt I'd found home, so to speak. It was like, you go to college or graduate school and then you leave there, then all of a sudden you discover this conference and it's a place to continue your education and continue your socialization, so to speak. What was not your first reactions, but your more mature reactions in the last decade or so?
Well, it's always been both inspiring and educational. It's inspiring because you see people, it's wonderful to see people that know so much more and are so much more creative and so much smarter than you are, to see what they can create, because it's just inspirational to see that. Oh man, that is so good what they're doing there. How did they figure out how to do that? It's the things that make you want to do better and to do more. And it's educational because of the courses and the technical papers and the panels all bring information from a lot of sources that you just can't get otherwise. I mean, it's not the same thing as reading online. I mean, unfortunately, we've all had to do Zooms for the last, couple of SIGGRAPHs, but in the future, we'll be back together again, and face-to-face interaction is important to us humans.
You've taught and been an educator and been a pioneer. Do you feel that the young generation, the youngsters who are in high school and college, have the kind of initiative that folks like you had 40, 50 years ago? Are we able to sustain the kind of intellectual and can-do development which the country has been so famous for?
Well, that's a good question. One of the things that I've enjoyed seeing is the maker movement, where people are creating robots, 3D printers, using 3D printers to create other types of gadgets. That sort of hands-on creation of combination of electronics and mechanical engineering is really interesting. And yeah, I think the kids really enjoy doing that. It's easy to get sucked into the trap of being a content absorber and not being a creator. But I think and so one of the things that's important is to see the kinds of content creation tools that let people who are let creative people be able to share their vision with someone else. And sometimes that's limited by the hardware that we have now, but it'll change. It won't in the future. I mentioned of, how do we create the really compelling virtual reality experience that will make everybody want to have virtual reality as opposed to being a novelty. And, outside of maybe outside of shooter games, I don't know.
We have time for a couple more questions. So the first one is, as a inventor and engineer and manager and company owner, what words of wisdom can you give to a person, whether they're our age or whether they're 50 years younger, who is thrown into having to or charged with the task of working with or managing a team of creative people to build something? What pearls of wisdom can we share with them?
Well, pearls of wisdom about managing. I don't know that I was ever a good manager, except that I saw as my mission to keep the rest of the company bureaucracy from screwing up the creative people that were making the products. That sort of line of defense maybe is one of the things. Hiring the most creative and talented people you can possibly find is so important. I think people that are jealous of talent are poison to an organization. So you really got to watch out for that. But I think the people that are really talented always like seeing other talented people and working with them, and are never threatened by somebody that's smarter. Smarter is better. Holy cow, we got somebody on our team that knows all about this or that or whatever. So I don't know that those are words of wisdom, other than sometimes you're lucky enough to find yourself in an environment like that, where I've been in corporate environments that were toxic, where people thought that the competition was somebody down the hall rather than, another company that they were supposed to be competing against. But
a young person who's thinking about starting their own business, they have a good idea, they have some artistic and technical skill. What can you tell them to help them have a narrow chance of success?
Well, you really have to look at it as a business. That is this something that people will pay you money for? Will they pay you enough money, or will enough people pay enough money so that you can keep on doing it? Because it's easy to think of something that from creating a business standpoint, as opposed to an artist standpoint. An artist needs to create a work that people are going to appreciate enough that they will pay enough that he or she can keep on living, right? A business, if you're selling software or selling hardware or applications or whatever it is that you're doing, needs to have enough people willing to pay enough money so that you can pay the rent. And you've got to look at your idea in that light. You may have a great idea, but if there's only going to be 3 people in the world that really need or want this, and they're not willing to pay much money for it, you can't really afford to put a lot of money into developing it. That's just the way it is. It's got to have some.
David Kasich, in an interview a week or two ago, expressed that one of the big problems in technology, he worked for Boeing, but I think it's probably the same in computers and the things that you do. He says is the scalability. He says scaling things up is usually much more complicated than it seems, and it is not easy to scale.
Oh yeah.
To comment on that.
Oh yeah. Well, I think Dave's exactly right. It's critical, but it's really difficult.
Let's start that answer again. Scalability is
scalability is critical, but it's really difficult. The last company I did, we took ideas from a research lab and we got them to the point where we could make more copies of it and we could sell those to research labs. but how can we scale that up? How can we make the technology so that it would apply to more, solving more problems, and more people would want it and more people could afford it? And that's a crucial thing. Sometimes you just can't do that. I mean, or sometimes it's really difficult, which often means it takes more people, more money, more resources, more time, which sort of boils down to more money.
I find my Macintosh has so many features that it is starting to, I don't want to be disrespectful to Apple, but become extremely hard to use, extremely unworkable, and very prone to failures. The wife and something as simple as iTunes and Audible books and her computer is endlessly having to resynchronize, re-download, rebuild. And it seems like we're spending more and more of our time chasing technologies which are supposed to integrate and synchronize all of our lives for us. Are we headed for a kind of a technological collapse in the near future?
Well, and you're talking about Apple, which is the company that supposedly has worked the hardest on creating a seamless experience between applications and devices so that you don't have to worry about any of that stuff. People in the PC world, Windows world, have it much harder, maybe. Things that are hard to use won't catch on, unless they're absolutely necessary. All right, unless they're necessary to life and your continued existence, you'll do whatever's necessary for that. But if it's something that you want to use as a tool, you're right. You can't spend your time, 50% of your time, trying to make the tool do what the heck it was supposed to do in the first place. You'll go back to doing it an older way, which may be less efficient, but
you probably built drag racers. You probably built drag racers with electronic ignitions when you were young.
I still like the mechanical types, yeah, rather than electronics.
And now the car is
my hobby these days is working on older, complicated technology. So radio equipment that's got 70 or 80 tubes in it, doing stuff that you should be doing in digital logic, but it wasn't available at the time. Teletypewriters that have got hundreds or 1,000 mechanical parts that are doing things that you'd be better off doing in digital logic. But it's really interesting. There was a lot of hard engineering that went into the revolution that happened in the 50s as the beginning of the computer age happened. And that just keeps right on going.
I was never very good with a manual choke, and I do have some appreciation of pushing a button to start the car.
There's no question it makes things easier, but there are a lot of us that just like sort of the challenge or the puzzle solving part of working on things like this.
Any challenges you want to lay forth for the younger generation who are going to watch this when we are both even older than we are now?
I guess the main thing is to try to put yourself in someone else's shoes. You're not just creating a product or an animation or something for yourself. You're creating it for someone else. Sometimes that someone else will be a user, particularly in the case of hardware or software products, or there will be somebody who experiences the animation that you've done, and you're trying to convey a feeling or an emotion or a story or an idea to them through the animation. But you've got to think about how they look at things. So it's one thing to say, yeah, if this doesn't work, I'll just change the wires over here to make it work. All right. Well, that worked for me, but that wasn't going to work for you, right? I had to think about, well, what if Judson was using this device? How would Judson want to use it? How would a million Judsons, 1,000 Judsons want to use this device? Put yourself in somebody else's shoes. I mean, that applies to an awful lot of things, but particularly if you're thinking about the development of technology, the development of products, the development of art, the development of animation. You've got to think about, well, the viewer's the user's standpoint, not your own.
Well, thank you for talking with us and talking with me and participating in the SIGGRAPH project. I know that your words will be valued, and we look forward to seeing you again in post-COVID era.
Well, I don't know whether it'll be valued or not, but if it nudges somebody just a little bit towards doing something that they otherwise might not have done, it'll all be worthwhile.
Adios.
Okay, so long, Judson.